another episode of No Orientation Programming. I'm Joe, and in this episode, we will talk about transmission lines. At least, yeah. I would like to begin with a couple of diagrams today, and I want to make a brainstorming more or less. What is a transmission line? I'm a software developer, so I'm not very I'm not an expert in electronics, but I like the topic. I saw a video of Veritasium, and I think you know him, big YouTuber, and he made an interesting video, and it was quite thought-provoking for me, and yeah, it's a very interesting topic. How the current actually behaves. What is the current doing? What is it really doing? And I tried to. I saw another video. He suggested a video of Rick Hartley, I guess. Rick Hartley. No, Hartley. Yep. Yes, this guy. He's an expert in PCB design. And this guy suggested another a book. One moment. Rick Hartley suggested a book. It's called Fast Circuit Boards by Ralph Morrison. It's quite expensive. It has a lot of typo errors, and it's thin, but the information in this book is quite valuable, and therefore I would, if you like the topic, then I would recommend it, I guess. It gave me some interesting hints. So, but in the book, Ralph Morrison wrote that it is hard to visualize what is going on actually on a transmission line. But I think the waves which are traveling along the transmission line can indeed be visualized a little bit better. I saw a lot of videos of another YouTuber. He calls himself, I think, 3 Blue 1 Brown. This guy is amazing. And also another YouTuber, I think Freya, I think. Nope, that's the wrong one. Nope. How is she called? She also makes very cool videos. About Bezier curves. Freya Holmer. Yeah, Freya Holmer. Freya Holm. Yes, that's her. That's her. And this is 3 blue, 1 brown, and these two Ubers are experts in visualizing stuff. As you can see, yeah. I would recommend to check out the videos or the channels, and I think three blue, 1 brown also has developed an engine to make animations, an animation engine. One day I will try to learn the language a little bit. It seems to be very interesting. I mean, he makes the videos with his own engine. So it's called Manim, yeah, Manim Mathematical Animation Engine. Maybe it can be used to visualize the behavior of the current. One day, when I have enough time, I try to learn the language a little bit. Because it's cool. Today we make simple pictures with LibreOffice Draw. And yes, as I said earlier, I want to make some brainstorming stuff. Nothing more. How I see the things. As mentioned earlier, again, I'm a software dev, so I'm not an expert in electronics, but maybe it's useful for some of you. Also, I want to make an kind of template for visualizing this stuff. Black. So we have a transmission line. A transmission line is, oh my god, I have to. Yes, error style. Yes, I have to relearn the. Yes, that's fine. I have to relearn the Office Draw. Nice. Okay, so I would like to see this left part as an supply, voltage supply. Like that. Yes, hopefully this is fine. And yes, that's a long line. That's a very long line. I have bought some cables for 30-meter coax cables to make some tests. Because I'm so curious if this is actually how I think if this is working how I think it is. So I make a little x because I want to simulate a switch, and then copy this thing Yeah, and now this X, little bit too big for me, for my taste. Okay, I can group this, I guess. Group, yeah. Now I have a fine X. Maybe I have a, I guess I have an X here, but okay. An X simulates an open switch. If the X is not here, oh, not here, then it's then this space is closed. Then I visualize. So that's it. So I want to make sure that this space is fine. Okay, okay. This style, I want to make the color more like custom color, more like this. Yeah, a little bit darker. Custom color, a little bit darker. How about? Yeah. Okay. Yeah, that's fine. Okay. A little bit thicker. Yes. Okay. The era style is cool, but it's a little bit too large. Position and size. Height. Oh no. Position width. How can I use this style? Here I think I can line. Oh, come on. The arrowhead can can be changed. The size of the arrowhead can be changed. But I forgot where. So connector. Line area, no. Font. No. Position and size. Line. Yeah. Start style can be another. Ahead. Arrow styles. Yeah, arrow short. Modify. Come on, they changed it. Okay, let's see. LibreOffice Draw. Arrowhead size. How to change things with, yeah. Line. Arrow style, yeah. Here. Nice. I am blind. Come on, so, but here I don't see it, so okay. Whatever. So, Yeah, that's cool. That's cool. That's cool. So now I make a copy of this. Yeah, and then I make a couple of these here. Yeah, nice, perfect. So what is this? This is the electrical field. So let's assume that this is a voltage, a constant voltage source. Then streaming. Yeah, yeah, okay. Transmission lines. And first. So this is at time 0. And we have a voltage supply text box. Or way too big. 10 const voltage supply. No. Yes. Okay. Const voltage supply. Yes. Okay. Let's keep it that way. Okay, on the left side we have ignore. Yeah, fine. On the left side we have a constant voltage supply. We have here an open switch, so there is no current flowing at the moment. We have a very long line on the right side, and for example 100 meters or so, and the end is open. The end is open, and as we know, the information of the electric stuff is not. It takes some time. It's traveling with the speed of light. So the interesting thing is, what is the current doing at the beginning? If we open the switch. If we have a constant voltage supply, this means that the current can be variable, yeah? So at the first stage, it looks like this, I think. As I said, it's just brainstorming. And now we remove the switch. Then what is happening now, in my opinion? This electrical field. Okay, we can make an E. Want to make an E like that, and this is E, and the color of E is custom color. Oh no, I want it to be the same color as this, and of course you can I can, yeah, I have a recent stuff, and here, yeah, perfect. Come on. Yeah, nice. So unfortunately, I'm not able to make an error on top of E. I would like to make an error on top of E, but because it's a vector field. But okay, let's keep it that way for a moment. Yeah, perfect. And That is okay. So now the electrical field is extended to the constant voltage supply, the voltage source, as I call it voltage. Yeah, voltage source, and that's const E. And variable B. Okay, fine. So E is constant, and the voltage source is extending this electrical field into the transmission line. But for this, it needs current. It needs current, and this current comes from the voltage source. So let's see, how can I make this? Oh no, yeah, like that, and copy like that, and then we have a red one. Yes, that's fine. Yes, that's cool. A current flowing out of the voltage source, but it's going in both directions. So current goes out and in. Now I hope I can make a round error. I would like to make that looks quite fine. Yes, nice. Please. Yeah, perfect. That's exactly what I want. Exactly. Okay. That's cool. Okay. So again, I want to make it a little bit more beautiful, like that. Then the end should be here, and this end should be here. That's fine. Then it should be red. It should be a little bit thicker. Yes. And error style this. The error is a little bit too big. Again. Yes, that's fine. Okay, so every current produces an magnetic field. And if it's going in one direction, then the right hand rule, I guess, is applied, hopefully. And this current, if there is current here flowing on this line, then the current is also flowing on this line. of course. So I make a copy here and here. Yes, okay, that's fine. So, and we know that the same. So now how can I rotate? How can I rotate? Yeah, here. Nope. Flip, arrange, convert, align, position, rotation. 180 degree. Perfect. And then the same in this direction. That's fine. That's fine. Yeah, well, perfect. So we now know that the current is going into the transmission line and coming back. But what at this point there is no current flowing. There's no current going into at this moment. There's no current on this position. So the current must go to another direction. And the direction is here. From the top line to the bottom line. From top to bottom. So this actually is a current that is called the displacement current. Minus. Okay, that's incremented. Minus 90 degree. What are you doing? 270. Okay, no. So that means what is this telling us? We have that the voltage source is loading the transmission line, and loading means to establish the same electrical field as in the voltage source. To change an electric field, to change an electric field, you need a displacement current, and the displacement current, or a different way, if there is a change in the electric field, then this can be seen as an current, and this current is dependent on the material it is flowing through. So this is very interesting and very important, because I think usually current is associated with electrons and particles, flowing of particles through space. But if an electron is changing its position, then the electrical field at this point, at any point here, for example, the strength of the electric field is changed, and therefore this position also sees the change from the electron, and therefore the change of the electric field can be seen as a current. Another interesting thing is, so we have a lot of errors, and I put 2 additional errors here. This black arrow is the direction of the wave. The wave is traveling with the speed of light from left to right. As soon as the switch is closed, the wave is traveling. A current is establishing the electrical field along the transmission line. And there is another thing that's called the Poynting vector. The Poynting vector is the cross product of the electrical field and the magnetic field. This is the Poynting vector. And this tells you in which direction the energy is flowing. So this is E. Then we have B. What size did we have here? 12. 12, and this is color red. This is B. I think B and not H, hopefully. So this is B. And then we have another error, and we make this error style dashed. Yes, and we make it color green. A little bit darker, yeah, dark green. And this is the Poynting vector. This is the direction of the energy flow. This is the direction of the wave. This is the wave. As I said, that's just brainstorming here. I don't claim this to be correct. If there is anything wrong with it, please tell me. So this has 10 and this has 8. Let's make it 8. Okay, 8 BE. That's fine. So, and that's that above is the energy. Energy. And also 8. And the energy, we make the energy green. Green energy. Perfect. So the energy is also moving in the direction because the voltage source is providing energy and pumping it into the transmission line. That's fine. That's fine. So the first interesting thing for me is the following. That arrow is I. That's the current I. And which current is flowing here at this moment? That's very interesting for me because the current that is flowing is following Ohm's law. Was like V is R times I. And that means R is V, no, I. I make here an I, and I make here a V, a small V. I is, I make it a little bit bigger this time. No, not yellow. Ooh. Perfect. So 12. Yeah, that's better. So I is, come on, I hate all this correction. I hate this correction. Oh, no, come on. Disable autocorrection. I hate this so much. I hate autocomplete. This is so bad. So, come on. Tools, autocorrect. While typing, tools. Automatic correct option. Disable everything. Options. Don't do that, please. I is come on. Come on. Oh, different version. I want to disable the whole thing. Come on, everything. Just do it. Ha. Okay. I is V divided by R. But R in this case is set 0. And one moment, please. One moment. I don't know. At some decrease font size, no. At some place I can. Whatever. Okay. C0. What is set 0? Set 0 is the characteristic impedance. Characteristic impedance. Characteristic. Almost. Characteristic impedance or surge impedance, usually written Z0, is a uniform transmission of a uniform transmission line, is the ratio of the amplitude of voltage current of a single wave propagating along the line. That means to not go to I don't want to go too deep into this at this moment, but Z0 is like a resistor, not a resistor, but a resistance, an impedance that is telling the voltage source. It's depending on the cable, on the transmission line. It's depending on the transmission line how much current at the initial instance, how much current there is flowing. And that's very interesting because that means it's not depending on the load. The current at the first instance is not depending on the load, but on the geometry and properties of the line. That means at the very beginning, some random current is flowing. And this current has nothing to do at all with the load on the other side, because this is a very long line, and the information how much current we need cannot be transferred with unlimited velocity. So we just don't know yet how much current it is needed on the left side. That's very interesting for me, because there is a wave traveling from the left side to the right side, and with a certain amount of current that is establishing the electrical field. Now, so this is a random current, a start current, and this wave is now traveling from left to right. The energy is also traveling from left to right, and the transmission line is loaded. And loaded means current is flowing here into the transmission line and then down here as a change of the electric field. Here we have electric field, and here we don't have an electric field, and the change here means a displacement current flowing, and a current of whatever type, if this is a flow of electrons, generates a magnetic field, and also the displacement current, the change of the electric field, is also producing an magnetic field. So, and I think that's the big thing Maxwell discovered, that he said not only the travel, the movement of electrons, of particles, creates a magnetic field, but also the change of the electric field. It was known that the change of the magnetic field is producing an electric field because somebody moved a magnet near a wire, and a voltage change was noticed. But it's also the other way around, that a change in the electric field is producing a magnetic field. Yes, so that makes quite sense, because we don't have a current flowing here, and we have a circle here. And I think that's very important, because I think it, for me personally, I think it's important to see current as a circle, not as something that is only going into one line. It's always going in some kind of circle. And the Poynting vector, the energy, this is the Poynting vector. And this Poynting vector is, as I said, the cross product of the electrical field and the magnetic field. The magnetic field is going here, in front of the line, here, and then backwards here. And that means the electrical field points down, and backwards the magnetic field. The electrical field is pointing downwards and the magnetic field is pointing backwards, so the pointing vector, the energy vector, is pointing to the right side. But this is also working on the bottom side, because here also the electrical field points downwards and the magnetic field goes backwards here, this point. And that means the energy flow is here on all the points here, it's flowing on to the right side. So now the wave is traveling. The current establishes the electrical field along the line. Yes, so, and this is going until this is working as long as we are not at the end, and at the end something is changing. Yeah, come on. So we need these two and we need these. I don't know. Let's see. 1, 2, 3, 4, 5. Let's see. Yeah, that seems to be fine. Yes, perfect. Perfect. Nice. Okay. Oh, very nice, very nice. So, now the strange thing we have here is when the wave reaches the end, then we have some problem, some situation, because some different situation. One moment, please. Oh, come on. I want to make it a little bit shorter. Do I really want that? Yes. Okay. That's fine to me. Okay. So, we have reached the end. But now we have a strange behavior. Because there can't be a current flow at this end, of course. Here is the end. There is no current can go here. So it should stop, but it can't stop. The electrical field is established as we see here. So no current should be flowing anymore, because the electrical field should now be the same as from the voltage source, but we have a little problem, because the established magnetic field can't go away immediately. I didn't mention that I assume at this point at the first the first scenarios assume that there is no loss, no resistance along the line, transmission line, so this is all lossless. And now we have the situation that the magnetic field can't stop as long as it's not forced to. And because of that, it still forces a current to flow from here to here. But that means that the electrical field is doubled. And this also means that the energy, there is an energy stored in the magnetic field, and that means that the energy from the magnetic field is converted into an electric field. Electric field is a potential, an electric potential energy. So in the next time frame, so this process has reached the end, and it's not stopping at this point. How can I please add new spreadsheet? Nope, this was not what I wanted. I want another page. Insert page. Page number. I am a total noob. I'm a total noob. How can I add another page? It's so relieving that other people have the same problem. Intro does not flow in the manner of content in right. The draw is like impressing that is used as side like discrete rather than page like flowing. To present content, it is a general drawing rather than writing application. The usual method of achieving intro does not flow. Yeah, great answer. Blah blah blah. Insert new slide. Insert. Image chart table media. Object. Snap. Layer. Blah 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 blah. Page. New. Come on. Page. New page. Thank you. Copy. Yeah, fine. So. No, come on. Sometimes I love this application, and sometimes I don't love it. So, okay, we have forgotten these two. No, I don't want to remove these two because they are very important. it looks like, because it looks like there is no energy flow anymore, but there is. So oh man, come on. There is an energy flow still happening, because as we can see, we still have an electric field and a magnetic field. And as long as we have both, there is a energy flowing. So we make a copy, and here we make a paste. So as mentioned earlier, the magnetic field can't stop immediately, and I've forgotten something. Oh no. Okay. But that's fine, that's fine. So I also want to show you another thing. That means this representation is not enough. Yeah, perfect. Now it's fine. Yeah. So I want to add something else. That means I want to, on the top side, I want to add a representation of the voltage. I have an I, yes, and I have forgotten the V. The V is here. V, I think it was 12. 12. This is bold. Why is this bold? Didn't activate bold, did I? Come on. So at this side, we have a representation of the voltage, and the representation, the dashed line is the 0. Long dash, yeah. That's not beautiful. Better. Okay, so yes, perfect. As you can see, we have a voltage source. At the beginning, we have along this part, we have a voltage of high and of whatever. And that's too high. Yeah. Too high, a little bit too high for me. So I need to stop. Okay, so we have a voltage of whatever. It's not important, but here we have a constant voltage, and here we have 0. And now this thing is changing. It is changing. It is traveling from here to here, and this is the wave front. So that means the voltage is established along the transmission line. At first we were here, and now we are here. And This is not stopping, of course. Ooh, where is the end? Where is the end? I hope the end is here. Yes. Nope. We are not fine here. So, come on. Yes, now it's working, I think. Come on. Yes, hopefully. So, and at the end, the whole line has the same voltage. But as I told you, it is not stopping. The magnetic field is not stopping. An electric field and an inductance. This is an inductance, and it tries to keep the current flow constant. That means there is still current flowing, as I mentioned earlier. And now the wave is traveling in the other direction, and it is loading the still loading. It's overloading the electrical field. That means that it puts additional errors in between. So it pushes the electrons into the transmission line, and here the current flow is stopped because the electrons are so packed there is no way out in any direction. So it's going backward and pushing the electrons in. And now the energy is still flowing into the transmission line. That means the direction of the energy flow stays the same. Stays the same. Energy flowing is flowing into the transmission line. Still moving into the transmission line. Range, bring to font. Is it better? I think I make it like that. The energy, yeah. Oh, that's better. That's way better. Oh, come on. Yeah. So the wave is traveling into this direction. At first, it's moving to the right. I always need to make it perfect. It's so it's very bad behavior. So okay, I try to copy and paste, come on. So, energy flowing is to the right and wave is also going to the right at first. But then this thing is changing. Here. The energy is still flowing to the right, but the wave changed its direction. It's flowing backwards. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the direction of the wave and the energy is now in the opposite. Energy is going into and the wave is coming back. And of course, until we reach this, now we have to also change this. From here to here, because the voltage is doubled. The energy that is stored in the fields is cut in half. Half the energy is in the magnetic field and half the energy is in the electric field. But the energy of the magnetic field is converted to electrical field energy. The electrons are packed into the transmission line. At least here, and on the opposite they are pulled back at this point. So it's more like a switch of electrons. So, and this is going until we reach this point. Until we reach the voltage source. And as soon as we reach the voltage source, we have this situation. One moment. The energy of the magnetic field. Yeah, perfect. The energy of the magnetic field is no, 1, 2, 3, 4, 5. Copy, paste, paste. The energy of the electric field, of the magnetic field, is converted to electrical field energy. And that is because when we reach this point, when we reach this situation that the transmission line is fully loaded, then at this point, when we reach this point, this edge of the right side, then at this time instance the voltage source should earlier. I think at this point, when the wave reached the middle of the line, then the voltage source should stop the current. I think at least at some way the voltage the loading process is finished and the voltage source must stop to send current. But we can't communicate this need of energy back to the voltage source. This excess of energy. We cannot communicate this excess of energy to the voltage source immediately. So it's still pumping energy into the transmission line too much. So the wave is coming back. The energy is going in and still going in, and the wave is coming back. And now the voltage source is confronted with the situation that it's pumping inside, and then it's seeing, oh, it's too much electrical field energy now in the transmission line. We have the opposite situation than at the beginning. The voltage source saw a difference of voltage, so it tried to, and the voltage on the outside was lower than the voltage on the inside, so it tried to establish the same electrical field on the outside as in the inside, and this is done by an outgoing current here. And as soon as we have this situation, it's kind of it's similar. It sees it's too much, and then this direction is changed. The direction of the current is changed. I remove the E and B fields because I think no, I don't remove them. The direction is now changed. That means the voltage source is now sucking the electrons out of the, oh, come on. Out of the transmission line again. So it's too much, and now it wants the opposite again. It's sucking the energy out of the transmission line. So, and this is done by lowering the electrical field. So now the wavefront here, I think the energy was going here. Which state should I display here? Which state? I think one moment, I have to think which to be equivalent with the old situation. Yeah, make it like that. So, and the electrical field is removed. How many arrows do we have? This 1, 2, 4, 6. Okay, 6. And this is done by an inverted current. So this 1, 1, 2, 3, 2, 3, copy, and paste at any point. Okay, where I copied. Okay, so on this B, remove it, removing this B, and then not removing this B, removing this B. So, and this is fine, this is almost fine. Here we have the current lines. Okay, perfect. It's the magnetic field. Magnetic field has turned around. Now it's going into the opposite direction, as well as the current. This thing must be grouped, for example, and the side, the direction 200 and 180. So now it looks like that. At first, the magnetic field was going from into this area, and now it's going out of this area. And going out of this area means that the wave is now going into this direction. And the energy is going outside of out of the transmission line. Yeah, perfect. So so again, the wave went back and stopped here, and now it's going again to the right, but the energy, the pointing vector, has now changed its direction because the direction of the magnetic field changed, and the direction of the electrical field is the same as before. So a current flowing in this direction, meaning is a decrease of the electrical field energy. So the electrical field is removed, part of it, not everything, and this means it is again like that. The voltage source always tries to establish the same electrical field on the outside as it is in the inside, and for this it has the ability to move the electrons around the current. So it's going back again. Only this time it's sucking the energy out of the transmission line because it has pumped into too much energy into the transmission line. So, and as you can guess, we have now a situation similar to here. So, what did I do last time? Come on. Insert. I forgot what I did last time. Insert. I can't believe it. I have forgotten how to add another page. Insert. A page. New page. Yeah, so perfect. So it must be the same situation like that, except come on. I don't like this. The fuck? I give up. Okay. Whatever. So, we had the situation that the energy and the wave have had a different direction, and we make this here, and here we remove these lines, and we move these lines, these arrows here. So, we remove them, put them here. Perfect. The energy was sucked out of the transmission line, and we had the situation that the magnetic field had the opposite direction. And the same here. This is so bad. I don't like graphical tools. So, yeah, fine. So the magnetic field was had the opposite direction, and like that. Yes, so the energy was sucked out of the transmission line. And now the interesting thing is that we have again the situation that the magnetic field, that the inductance of this transmission line can't stop the current. Can't stop the current. The current is still flowing. That means, and because there are no electrons and no electric field here at this point that can be distracted, means that something else, there must be a current must be provided by something else, and that is done, of course, with with the energy of this electrical field. And now we have again a situation like that. No, I think I will make a copy of this. It's faster. So, come on. Okay. So, how many did I remove? I can't tell. I take 3. 1, 2, and 3, and 1, 2, and 3, and this current is still flowing. And this current is removing. This current is removing is removing the electrical field, the remaining electrical field. That means we are again, the energy is still flowing outwards, and oh, come on, this is so bad. Come on, why? Energy wave, energy wave, energy. I want, when I paste something, I want the pasted stuff to be at the mouse cursor. This is so strange. So I don't want to search it along the spreadsheet. So the energy is sucked out again, still for a long time now. So, and the wave is now again traveling in the same direction. And as you can imagine, this process is going until this wave reaches the end here. And then we are at this point where the one moment. Oh, yo. I need some vertical diode here. Zack. zack, this the zero line. The zero line and the zero line is here. Yep. And then another one here. Yep. So that means all the energy that was stored in the transmission line is now sucked back. In my opinion, so I don't claim this to be correct, but I think that if you don't have any losses, then you try to push energy into something, into a transmission line, that it bounces back. You can't it bounces back the whole way up to the beginning. You can't put any energy into the transmission line if you have no losses. So this was kind of a brainstorming session. I will put this in a Git repo. Maybe somebody of someone of you can tell me if there is anything wrong with it. I'm quite satisfied with how I think it is, but maybe I'm completely wrong, but hopefully it's not completely wrong. So the reason I have ordered the cables, I want to see at the oscilloscope what's going on, and yes, so this session I will extend this session someday. I want to see how it behaves if we have losses, and I want to see how it behaves if we don't have a wavefront like that, but a smoother edge. And what's the difference having an edge like this or an edge like this? From the video of from Veritasium and from Rick Hartley and Ralph Morrison, from the book of Ralph Morrison, they told me an interesting thing, and that is two things. Ralph Morrison says, and Rick Hartley also, they say the energy is in the fields and only in the fields. And the second thing is it's all about the rise time. The rise time compared to the time the wavefront travels from along the transmission line. If the rise time is very long, longer than this longer than the time it takes the wavefront traveling from left to right along the transmission line, then everything is cool and easy. But as soon as the rise time is similar or much lower than the traversal time, then stuff is going to be strange. Then it's emitting something and and affect something, other components. So yes, that's how I see it. As mentioned, I'm a software dev. I hope it's useful for somebody else, and I will make some nice pictures and later. And yes, so did I forget something? Ah, ooh, I said this is the B field, but I think it's the H field. The BH field. Magnetic field. So must be a magnetic flux in how they account for magnetization. Come on. Oh yeah, I think E and B. Okay, E and B. Yes, E and B. Hopefully, and H. H is compared to electrical field. Electrical field. The E field, yeah, the E field, and there must be another field. Not the B field, but the D field. The D field, the definite equation. Yes, the D field is there. E and D, as well as B and H, are connected through the material constants. So they should be compared with each other correctly, and you can see them in the Lorentz force law. The E field is quite similar to the B field, and on the other hand, the D field is somewhat similar to the H field. The one pair is in the electric world, and the other pair is in the magnetic world. So, yes. Yes, perfect. Okay, so I don't have to, but this is can be removed. This is okay. Here is okay. Here is okay. Okay. So, I'm quite satisfied. And let's see. Print. Oh, export as PDF. Export directly as PDF. Don't know what that means. So, okay. So, yes, committing, and then the session for today is done. I guess it info screenshot. Yep. Yes. This was the screenshot from a YouTube video. I can, yes. Add oscilloscope screenshot. Add first transmission line document. So this, yes. Okay. This is some some material to make a discussion the next episode. This is the use of it. Okay, energy going in, wave going in, energy going in, still energy still going in, wave going back, still here the same, overloaded, voltage source decides to remove the energy again. No, this is not correct, because then we need to if we flip this error, then we have to flip this error. I flipped the errors too early, the current errors. I will make this. So I want to change this. So where is it? So this should be like this. Fine. Export as PDF. Yep, export and save. Yes. Back. Now it's working. Energy is still going in, wave is going back, energy is going in and back, but now it flips from this to this. Every time this arrow is flipped, also this arrow must be flipped, because the direction of the energy field, the electric field is staying the same, but the direction of the current and the magnetic field changes, and so changes the energy, the direction of the energy, and the wave is going into the transmission line again. This destruction of the electric field, removing of the electric field, half of it, but it's not enough. It continues to suck the energy out of the transmission line, and therefore the remaining energy of the electrical field is removed. The wave is going backwards again, and this is going as long as every energy of the transmission line is removed, and then we have this situation again, and then the whole process starts again, moving into the, because it's again not finished. Okay, yes, I think I'm happy with it. So so everybody, I hope you enjoyed the session a little bit, and next time we will I don't know what we will do next time, so I will yeah, let's see. Hope to see you again, guys. Bye.